today we are happy to have Jian Song from Rutgers who came to tell us about RCD structures on singular Kahler varieties. Thank you.
Thank you, Simon. Thank you, Max, for the kind invitation. It's my great pleasure to speak at CMSA Geometry Seminar. I'll talk about some recent development and work on RCD structures on singular Kahler spaces. Since it's in the CMSA Center, so it's also a little bit related to, hopefully related to physics and some related to Kahler manifolds. It's joint work with many people, many collaborators. So you see it on the slides in the theorem. Let me first get the outline of the talk. Well, first I'll give some background, especially the classical C0 estimate of Yau's celebrated work solution to the Kahler conjecture. Also, the partial C0 estimate of Tian, and also in complex dimension 2, and then the fundamental work of Donaldson and Song on the geometric differential and algebraic geometric relations for projective Kahler manifolds. Then I'll talk about our recent results on geometric estimates on singular Kahler spaces, turning the analytic PD results into geometric estimates. And then we'll talk about global geometric and analytic structures, particularly the RCD structures on such singular spaces. In the end, if I have some time, I'll talk about applications. So let's first take a look at the classical complex Monge-Ampere equations. We assume that X is compact closed Kahler manifold without boundary and with complex dimension n. So the real dimension is 2n. And little theta would be a smooth Kahler metric on such a Kahler manifold. So theta is a Riemannian metric and also a symplectic form, and it's also it's a closed 1-1 form. And it gives it has both the symplectic structure and the Riemannian structure, and also compatible with the complex structure of X. And then we choose a smooth volume form, big omega. This is a smooth volume form on n. It's a positive real 2n form on X. And for simplicity, we can rescale omega such that the total volume of omega is equal to the intersection, the top intersection number of the Kahler class stabilizing. Or you can just, on the right-hand side, you just integrate theta to the n over X. They're the same. This is for normalization. Since we have this normalization, we can look at this complex Monge-Ampere equation. Theta plus dd bar phi, which is again a positive 1-1 closed form, and you take the top power, the dimension of the complex dimension of X, and it has to be equal to the prescribed volume form. And we can always assume the solution phi is equal to 0. So this is the standard complex Monge-Ampere equation on a closed Kahler manifold. Right? And we have the famous solution of Yau in 1976 to the Kahler conjecture. The theorem says there exists a unique quasi-Fourier subharmonic function with respect to theta, and which is also smooth, solving the above complex Monge-Ampere equation. Right? So in particular, if X is a Kahler manifold, the first chain class vanishes, and you choose the holomorphic volume form, then this is exactly gives you, given any Kahler class, it gives you a unique Ricci flat Kahler metric. Right? So this solving Monge-Ampere equation obviously is closely related to geometry and physics. So the key of Yau's solution is the C0 or infinity estimate, L infinity estimate for phi. And Yau's approach is by the Nash-Moser Mori iteration. Okay? So this is the key estimate in Yau's work to solve Kahler's conjecture. Almost 2 decades later, there's a huge progress improving Yau's C0 estimate. So let me just go over the important work of Curvature in 98, as well as later generalization to the degenerate case by RCD, Gage, and Zeraki. So here, again, we have a compact Kähler manifold of complex dimension n. Here, theta x is a smooth Kähler metric equipped on x. And then instead of looking at Kähler metric, we only look at a so-called big positive form. This is a smooth closed 1-1 form. It's non-negative, and the total volume is greater than 0. So this is almost like a Kähler metric, but instead of strictly positive, if it's strictly positive, then it's a Kähler metric. But this one is not strictly positive. It might have some degeneracy. On the other hand, the degeneracy is not that big because the integral of theta to the n is positive. So it can only, in terms of class, a cohomology class, the vanishing part is only a subvarieties, hopefully, of x. Right, so you can view theta as sort of a Kähler metric away from a subvariety of x in the heuristic sense. Okay? And again, we choose a volume form such that this is LP. This volume form is no longer volume form, a volume measure. This is not necessarily a smooth one. You could have singularities, could have poles, could have log poles. We only require that the volume ratio omega is LP for some p greater than 1. Okay, so the right-hand side doesn't have to be bounded even. It only has to be for LP p greater than 1. And of course, you need the normalization condition such that the total volume of omega is equal to the top intersection number of theta. Then the associated Monge-Ampere equation admits a unique solution. You don't expect the solution to be smooth because the right-hand side omega is not necessarily smooth. It's only LP. And also theta could be degenerate. It's no longer a Kähler class. But you still get a unique solution, which is quasi-Fourier subharmonic with respect to theta. And also the solution is bounded. So it's a bounded solution. And this also tells us how to solve the Calabi conjecture in the singular setting, because here we allow the theta to be degenerate. That means x can be also singular, because once you have a singular variety, a Kähler variety, you look at the resolution of singularity, you pull back the standard Kähler metric, it becomes a degenerate Kähler metric upstairs. So this theorem, basically, you can generalize in various ways. For example, x is only assumed to be normal Kähler variety. That's enough. So this theorem generalizes Yao's original theory in many aspects. First, the right-hand side of the Monge-Ampere equation does not have to be smooth or even bounded. You only need it to be LP for p greater than 1. I think in the original work of Chen and Yao, for the smooth setting or the Kähler setting, they can manage to prove for p greater than 2, greater than or equal to 2. But now the key improvement is that p only needs to be greater than 1. This is, later you can see that this is exactly corresponds to the KLT category of singularities in algebraic geometry. So somehow this is where analysis meets algebraic geometry. And also the other catch is that x, since we require the theta to be only non-negative, so there's a lot of room to maneuver. You can even make x singular. So this is quite some generalization from the original solution of Calabi conjecture.
Do you have a favorite singular x to keep in mind?
X would be, in the future, we're going to look at a normal Kähler space or projective variety with KLT singularities. In the Calabi case, you can just, you can also just think of this as a Calabi variety with KLT singularity. That's also fine.
What is the condition in parentheses on phi? The
Phi?
sup
This
x?
one.
No, above.
Sup. We just, because you add a constant, you still get a solution. So we just normalize that the suprema of phi is equal to 0. Otherwise, the solution can always translate by a constant. You get another solution.
Just for uniqueness.
For uniqueness, yeah. All right, so as I said, Yau's theorem can be generalized to the singular setting, as well as the right-hand side being LP instead of a smooth volume form. So we can always, heuristically, let's say if X is algebraic or projective, and you can look at a Zariski open subset of X, we can assume that the theta, even though it's only assumed to be non-negative, it's scalar on a large portion of X, on the, let's say, on a Zariski open subset of X. And the volume form, even though it's LP, it might have some poles, log poles on some subvarieties, but again, it would be smooth on this nice big open set, Zariski open set X not. Okay. Then the solution would be, in most of the geometric setting, the omegas, the solution would be a smooth Kahler metric on a Zariski open subset of X. So when you solve the original equation, if you assume X is singular, if the data is nice enough, everything would be nice on a Zariski open set of X. For example, you only look at the regular part of X. So the solution is a Kahler metric, smooth Kahler metric. But we have no idea its behavior near the singularity, or near where the volume measure becomes singular or degenerate, or where theta becomes degenerate. So you have some small set where everything goes wild. But at least away from these small bad set, everything behaves quite nice. Because the regularity theory you can sort of prove certain regularity and show that the solution is smooth away from the singular set of X. So the natural question is, since omega is a Kahler, the solution is a Kahler metric on X naught, you can just focus on X naught equipped with the smooth Kahler metric omega, and of course the smooth volume form omega to the n, the intrinsic metric and the associated volume form. So this part is an open Kahler manifold. The singular set could be very wild. I have no idea what the behavior looks like. So why not just take the metric completion? And we just go, it could be completely different from X a priori. But for convenience, we look at the good part and we look at the metric completion. And we just write it as X hat. D refers to the distance. Mu refers to the volume measure coming from this metric completion. So this is obviously a metric measure space. So once you solve a singular Monge-Ampere equation with reasonably good data, then you get a smooth Kahler manifold on the large open set of X, the Zariski open set of X. Then you naturally take the metric completion. And you want to compare X hat to the original algebraic variety or Kahler variety and see what's the relation. There's no reason a priori that they should be equal. You don't even know that it would be a bounded space because the diameter could go out to the infinity. The singular set might possibly develop a pole or complete part. So no one knows.
Yeah, can you say, so you said it becomes wild or degenerate at the singular set. Should I think of it as a pole or a zero, or everything is allowed?
Everything is allowed. You only need the right-hand side to be LP. That's the only integral assumption. Okay, so the natural question of what is this guy? Does it have a nice geometric, analytic, and algebraic structure? So our conjecture is, if X is Kahler, normal Kahler space, or normal Kahler variety, and it has KLT singularity. KLT singularity is that once you resolve the singularity, the discrepancy, you have a bunch of simple normal crossing divisors. The coefficient is always greater than -1. That means essentially the pole has order strictly less than 1. But that's exactly corresponds to the LP condition for p greater than 1. So that's equivalent. So the KLT condition is exactly the LP condition for the Monge-Ampere equation for p greater than 1. And we assume that the Ricci curvature, the current, is greater than -1. But -1 doesn't matter, it could be any negative number after scaling. So you want the Ricci curvature as a current to be bounded from below. Okay? So this is familiar because in Riemannian geometry, we always look at the manifolds whose Ricci curvature bounded from below, and you look at the moduli space, you look at the degeneration and the compactness problem of it, like the Cheeger coding theory or the RCD theory. So our conjecture is that then you take the metric from the previous sides, you take the metric completion of this guy, it would go back to the original variety. They are homeomorphic to each other. So when you take the metric completion, it's not going to change the topological structure. It's not going to change the complex structure. But of course, the singularity, you have to look at its tangent cone. Then it becomes a bit more complicated. Right? So not only, this is like a micro type of a conjecture. Topologically and in terms of complex structure, they're the same. But you can also talk about microstructure by blowing up the singularity. And those tangent cones, in some sense, should also be unique. And it has a natural algebraic structure. Okay? So this is the general conjecture. And in fact, it suffices to show that this guy is an RCD space. This is by a very recent work of Zaklahidi. Okay?
I guess you should define RCD space.
It's difficult to define because I'm an expert. I don't know how to write down the precise definition, but I'll tell you exactly what it is in a few minutes. I'm not going to use the most general definition. I'll just use the definition for practical use. Okay? So RCD space, you can view it as just a generalization of the limits of from Cheeger coding theory. It comes from, it's more or less like the limits of Riemannian manifolds with Ricci curvature bounded from below without collapsing. That's it. But it's more general in the sense that in the end, you want to replace the Ricci curvature bounded from below condition by a more synthetic approach. Namely, as long as it satisfies certain weak Bachner identity, then it is RCD space. But don't worry, I'll get back to it in a few minutes. And also, let me talk about Tian Donaldson-Song's partial C0 estimate. Okay?
Very political on this slide.
I'm not going to comment. Anyway, so here we already fixed a Kahler manifold, a projective manifold, Kahler manifold X, right? And I pick Kahler metric in an integral cohomology class, right? It's in Z, but okay. And then we assume that the Ricci curvature is bounded from pinched from -1 and 1, and we also assume that the volume is bounded from above. Because it's a smooth Kahler manifold, it immediately tells us that the volume is bounded from below because at least it's equal to 1. This is in the integral class. So we are looking at Kahler manifold, n-dimensional Kahler manifold, equipped with a Kahler metric with uniformly pinched Ricci curvature and uniform diameter in the integral class. So this is a huge class, right? And then it was proved by Donaldson-Song that this guy, the huge space, can be embedded in the same big projective space. And the dimension n depends on n and d. Okay? So it's very, very strong theorem. Not only they proved this so-called partial C0. It's actually quantitative embedding. So I would also prefer calling this partial C0 estimate as quantitative quadratic embedding, because it can give effective bounds on the Bergman kernels, right? Both upper and lower bound. So our goal is to establish or develop a geometric theory for complex Monge-Ampere equations. Because if you're in the smooth category, then the analysis will immediately give you the geometric consequence because you have all the curvature controls and everything. But once you have degeneration, you're sitting on a singular variety and your volume form becomes degenerate, then you don't really have good function space near the singularity. What you do is have to look at the blow-up limit and tangent cones, and even you have to look at the diameters, the eigenfunctions, even the linear theory of such singular spaces. So our goal is to establish geometric theory for complex Monge-Ampere equations and turning the analytic estimates into geometric estimates. Right? So we want to turn Yao and converges our infinity estimate into geometric estimates. And we also want to turn generalize the partial C0 estimate in the singular setting, because by doing so, you can give streamline the proof of, for example, Yau-Tian-Donaldson conjecture, just using the continuity method without any variational approach. Okay? Because I think the compactness theory is essential.
So there is no continuity method proof of Yau-Tian-Donaldson conjecture?
In the singular setting.
Oh,
in the singular setting, so you don't have it. Right. So let me talk about geometric estimates on Kahler spaces. So this is very similar from our previous setting. We have a compact normal Kahler space of complex dimension n, and you have a smooth Kahler metric. When we say smooth Kahler metric on Xn, it means that locally it's a smooth metric pullback from the local embedding of X into some big Cn. So locally, it's just this restriction of a smooth Kahler metric on big Cn. Okay, then you can solve. We consider the following complex Monge-Ampere equation. The right-hand side is theta to the n, and E is e to the minus f. And we want to solve for this type of a theorem, especially for P. The right-hand side is LP. Okay, and F is L infinity. All right, so again, we know that the solution would be smooth on the regular part, on the smooth part of X, and it's a Kahler metric. Then we just take the metric completion on the smooth part of X, and this is a metric measure space. And X naught is an open subset of X hat. It's a Zariski open subset, usually. And on the regular part, this metric is locally isometric to the original smooth metric on it. So you have a local smooth amount. But the only problem that would come up is near the singularity of X. Right?
What does it mean, Zariski? X hat doesn't have an algebraic structure, does it?
No, but it's only a normal Kahler. But in the algebraic, in the projective case, so which I will focus on talking about, so it would be this open set, a Zariski open subset.
X hat was defined as a completion of a metric space.
Right, so that's what we're going to prove. So to show that, because here, the singular set X minus X naught is a closed subvariety of X. But then when you take the metric completion, it could be very wild. So we want, the whole point is to find the relation of X hat and X. Hopefully they're the same. Okay, so the analytic singularity turns out to be algebraic singularity.
I think the point is that X naught is only an open subset of X hat, not Zariski open.
This for the Kahler case, it's just open.
Yeah, okay.
Dense open.
Yeah, dense open.
Dense, yeah.
All right, so what we can show is that indeed the diameter is uniformly bounded. In fact, it only depends on the Kahler class and the LP norm of the right-hand side. So this basically tells us that, first of all, it's a compact metric space. The metric completion will not have a complete end, will not go off to the infinity. This sort of corresponds to the boundedness structure or theorem in algebraic geometry. Because the boundedness corresponds to, in differential geometry, is that you can't have a complete end. Everything is bounded. Okay? And second, we prove the almost optimal Sobolev inequality. For any exponent q between 1 and over 1, we have the Sobolev inequality, where u is in the W12 space of X hat. So we, in fact, established the linear theory for the Laplace equation on the singular space. Right? So we have the diamond bound, we have the Sobolev. The Sobolev would imply non-collapsing, but it's not going to be optimal, the exactly non-collapsing, because we don't have the q cannot be taken as n over n minus 1. It can be arbitrarily close to n over n minus 1, the optimal exponent, but not quite there. So there's a little bit gap over here. Okay. So the original theorem has a small degenerate locus assumption, but it was removed of being independent by us, and also by Gage, Tau, and Wu independently. So the consequence is that once we have the diamond bound and the Sobolev inequality, we can establish lots of estimates, like eigenvalue estimate, heat kernel estimates, and non-collapsing estimate. So again, it's not going to be 2n, it's going to be 2n plus epsilon. It's a little bit off, but almost there. And we have linear theory for the spectral theorem for the Laplace equation. So this, I think Yao in the 80s, they proposed that how to look at He kernel estimate and eigenvalue estimate on the singular space. But at that time, it was only considered an algebraic variety embedded in a big Cn. You use the Bergman metric to do it. But our catch is that we don't want to use Bergman metric because it's algebraic metric. We want to look at arbitrary Kahler current coming from the Monge-Ampere equation. The only assumption is that the right-hand side is LP. That's the only assumption. Okay. All right. So I want to make a remark that our theorem has no curvature assumption because usually, how do you get a diameter bound? You usually need a certain curvature assumption. For example, the Ricci curvature is strictly bounded away from 0. Then you have a diameter bound. But in general, you need sort of a diameter bound. But our theorem, the diameter bound is in a surprising sense that you only need a volume measure to be LP. That's the only the assumption. Even for Riemann surface, it's a little bit surprising. You just only look at the volume measure because of conformal class. You fix the conformal class. As long as the volume measure is LP, the diameter will be uniformly controlled. And we have almost optimal and non-collapsing subleft quantity. The exponent can be arbitrarily close to the optimal one, n over n minus 1. Here, n is the complex dimension. Okay.
So non-collapsing here means, well, you're obviously not talking about the whole manifold, right? Because your open set is the same. Non-collapsing means something very close to, yeah, but what it really means?
So it's the volume, the local ball, small ball, it's almost as the Euclidean ball, in the Euclidean volume. You have this epsilon.
I don't understand that.
You have a little bit. You don't reach.
Is that like a technical thing, or is that?
So it could be if it's epsilon is 0. This is the true non-collapsing.
Yes.
Right. But here we only have a little bit off. But still, you can use this. For example, the ball cannot collapse too fast. Okay, it can be flattened. The rate cannot be flattened too fast. It's almost like a Euclidean ratio, but not quite. But in order to go from almost optimal to optimal, you might need extra assumption. And this is where the curvature assumption would kick in. So you still need a little bit curvature assumption to turn this almost optimal subleft inequality into optimal inequality, or almost non-collapsing into real non-collapsing result. Okay. So this is where we hope the Ricci curvature lower bound would help us. Okay, so RCD structure. I'm new to this field, and I just going to sort of explain it in terms of in the Kahler setting. So now we assume in Xn is a projective variety with KLT singularity. In fact, even for the normal Kahler variety, as long as the KLT singularity, most of the result would be carried over. Not much difference. We defined a big set of Kahler currents on X, such that they're in the integral class. So it corresponds to an ample divisor or line bundle, ample line bundle. It has bounded a local Kahler potential, and on the regular part of X, it's smooth. It could be C2, it could be C4. C3 is enough. Okay. And the total volume measure, omega to the n, the top power of omega, is LP integrable for some p greater than 1. When we say LP integrable, it's with respect to the so-called canonical local volume adapted volume measure. You use the generator of the canonical divisor to define a natural volume. For example, in the Calabi-Yau setting, you just look at a holomorphic volume form. That's you compare to the holomorphic volume form, it's LP, p greater than 1. In fact, the condition 2 would be implied by condition 3. So 3 would imply 2 if omega n satisfy the Monge-Ampere equation because it's LP integrable from Courvoisier's theorem. We know that the local potential has to be bounded. We have another additional assumption now. This is new, the last one. We require the Ricci curvature as a current is positive. It's not. It's bounded from below by -1. So you can take a minus dd bar log of omega to the n. If it's a volume, you would say, well, how does it define? For example, in the Calabi-Yau setting, you just put a holomorphic volume from downstairs and add dd bar cancelled. But you're just looking at the quotient of omega n to the volume measure. It's a function. So all you needed is that this is pluri-subharmonic with respect to omega. So it just comes from the several complex variable definition of convex function, pluri-subharmonic function. Right? So in fact, you can define Ricci curvature as a current in this setup. Right? So even in the singular setting, we're not going to define near the singularity. We're not defining the Ricci curvature in terms of differential geometry, but as a current, okay, using pluri-subharmonic function. So here, the only new input is the lower bound of the Ricci curvature as a current. That's just after rescaling, we just assume it's -1. The lower bound is -1. Okay, so that basically says if you look at the Monge-Ampere equation, omega n equal to e to the minus f times the Calabi-Yau, let's say Calabi-Yau volume form. So this function f is quasi-pluri-subharmonic with respect to omega. That's all you need. So this is one way to define Ricci curvature on a singular space. This definition, of course, is different from the usual RCD theory. This is using the several complex variable to define Ricci curvature. So again, we go back to our conjecture is that if omega is in this special class, meaning that the volume measure is LP and the Ricci current is bounded from below, then you can take the metric completion of its smooth part. Then it will be homeomorphic to X, and it is an RCD space. Why RCD space complete? Because RCD space have tangent cones. That means after you take the metric completion, not only it's globally it's homeomorphic to X, also at each point you can look at the blow up of X. It also gives you a metric structure in the limit.
Is that how you understand they're homeomorphic? You look at like after taking metric completion, you look at the set which could be like a singular set, look at tangent cone, and see you get something smooth?
Yes. You have to first show it's RCD, then you have tangent cone. Once you have tangent cone, you can apply the local partial C0. So essentially, you're doing a local Kahler embedding, a quantitative Kahler embedding. So the whole theme is to apply quantitative Kahler embedding using a little bit PDEs.
Yeah.
So it's the geometric L2 theory plus singular Monge-Ampere equation. And also, if the Ricci current is pinched, bounded, not only bounded from below but bounded from above, the metric tangent cone of X will be unique. Well, they should all be unique, but then this should be the same as the algebraic tangent cones. So this is the generalization, should be the generalization of the work of Li and Xu, my colleague Shi Li and Chen Yangxu. And later work of Chen Yangxu and his collaborators. I want to make a remark that RCD spaces are just generalization of degeneration of Riemannian manifolds with Ricci curvature bound below, plus the non-collapsing. You don't want it to be completely collapsed. And this is closely related to the Cheeger coding theory and developed by Jean-Marc Villani, Stern, Ambrosio, Gigi, and Adam Baker. So in our setting, I didn't give you the definition, but I can tell you how to verify the singular Kahler space, when the singular Kahler space carries an RCD structure. Whereas in our case, suppose X is a projective variety with a KRT singularity, and you have the Kahler current, which is smooth on the regular part, with LP volume measure for some p greater than 1, and the Ricci current is bounded from below. Then this guy, the metric completion is an RCD space if and only if all the eigenfunctions with respect to the Laplacian of omega are Lipschitz. As long as they're Lipschitz, immediately you would know it is an RCD space. It carries the RCD structure. So this is simply by combining the work of Honda and our earlier work of Sobolev inequality plus the linear theory for the Laplace equation. So we have a good cutoff function, we have good linear theory, we have Sobolev inequality. Then you can immediately, the Lipschitz condition for eigenfunctions would imply a weak Bachner type of inequality, and you can get to RCD space. So for our setting, for the Kahler setting, all you need is to show that the eigenfunctions are Lipschitz. So quite analytical, but it's in general it's quite difficult to show. So there are many recent progress with additional assumptions, and especially in the past year, I think lots of works have been done in this direction. So I talk about more recent work with the joint work with Xin Fu and Bing Guo. So our result is that the conjecture holds for the case of complex dimension equal to 3. So let me rephrase it. Suppose we have a 3-dimensional projective variety with KLT singularities. Okay, and x naught is the regular part, and you have a metric in Rx, which means you have a Kahler current with Ricci curvature, Ricci current boundary form below with LP volume form for p greater than 1. Then the metric completion of the regular part as a metric measure space is homeomorphic to the original algebraic variety or projective variety x. And the singular set, the Hausdorff dimension of the singular set is less than or equal to 3, the real dimension less than or equal to 3. If the Ricci current is pinched, then every tangent cone of this guy is unique, and it's equivalent to the unique algebraic cone of the singularity of the original algebraic variety.
Is it like an algebraic geometric version of like Allard's theorem? When you look at, you get the same tangent cone, it implies they are the same space.
Not quite so, because in general, in algebraic geometry, it's very special, because you have to look at KLT singularity, then the tangent cone is.
I see. It's not very.
It's only recently proved that the uniqueness and the existence. So the original idea goes back to my colleague Chi, using the volume of the tangent cones.
Can you say how you get the upper bound on the dimension of the singular space?
The dimension, this one.
Yeah.
This is simply using, you look at the tangent cone, and you have the splitting. So because you would expect this is less than or equal to 4, because the singular set, this is the KLT normal variety, but you can't quite reach that. If the Ricci curvature is pinched, then indeed this is 4. But if you only have Ricci curvature boundary form below, at the moment we can only show that since the singular set, the Hausdorff dimension is less than or equal to 3. But possibly it should be just 4 as well. Oh, no, less than 2, sorry.
Yeah.
Less than 2.
Less
than 2.
So the real dimension
is,
because of the complex nature, you expect the complex dimension to be 1.
double. Yes, you want to.
Which is the real dimension would be.
Right. But then since you only have the complex dimension, for example, in general, you're not going to have, if you look at the Chico-Cone theory, if you look at the degeneration of Kahler manifolds with Ricci curvature only boundary form below, this is codimension 2, it should be 4, because you can think about Riemann surface. If there are only Ricci curvature boundary form below, you can't have conical singularity property logic. It's just codimension 2. Here it's codimension.
You can't even do strictly less than 3. I mean, because
strictly, I don't know.
I
don't know. At the moment, we can only show it's less than equal to. Because on the tangent cone, we can just split off lines, not too much. If the Ricci is pinched, then it's 2. The consequence is that it provides abundant examples of RCD spaces that do not arise as limiting space from Chico-Cone theory. From my understanding, that it's quite important for to find new examples in the RCD theory that they're not coming from the singular spaces, not coming from the Chico-Cone theory. So this now shows us, well, any algebraic projective variety with the KLT singularities, it can be realized by RCD spaces. So these singularities can be very natural, form a really large class. And then you can prove compactness theory for Kahler Einstein varieties. So we're going to establish the partial C0 estimate for singular varieties. So now we just look at the normal projective variety with KLT singularities, and we're picking up all the Kahler current in the integral class with the volume in LP for p greater than 1, and also the Ricci curvature is bounded from below. We also assume the diameter is bounded from above. We assume the volume is bounded from below. So this is new because they are not, even though they're in the integral set class, but the singular spaces, you have singularities, so you need the volume lower bound. And we want to establish the partial C0 for this big space of all of these guys, the metric measure space, induced by as the metric completion of the regular part. And so this is how it works out for the partial C0. You look at the line bound over X, the line bound's curvature is the Kahler current, and you pick orthonormal basis with respect to the kth power of the line bound, and with respect to the L2 norm, with respect to the metric of the line bound and the rescaled volume with respect to omega. Then you pick up the Bergman kernels. You take the norm square with respect to metric H. You take the huge sum. This is the Bergman kernel. And the key is that from Donaldson Song's scheme is that you want to have strict uniform lower bound away from 0. So this basically is kind of a base point free on non-vanishing theory, because this is how you prove Kahler embedding theory. You want to show there at least one section that does not vanish. So that's why this is a quantitative Kahler embedding. So the conjecture is that over that space there exists a unique constant C such that the Bergman kernel will be uniformly bounded from below and above. Okay. So this previous is this Bergman kernel. You look at all the orthonormal bases of the line bounders, and you take the norm square, and then this guy has to be uniform bounded up below and above. Especially this lower bound is placed essential, but because it corresponds to the non-vanishing from Kahler embedding. All right, so what we can show is that the conjecture indeed holds in complex dimension 3.
Is it trivial in dimension 2?
Dimension 2, not trivial. That's the work of Tian. He proved this Yau's conjecture for Fano's surfaces. Yeah. So that's highly not trivial. And in that paper, that basically lays out the roadmap of the partial C0, how the partial C0 should be established. And in fact, you have to look at the degeneration of the sequence of the varieties. And in dimension 2, the only advantage is that the degeneration, because you have the epsilon regularity, the singularity are only orthoform singularity, isolated orthoform singularity. That's the only advantage in complex dimension 2. So that means that as long in dimension 3, all of these guys with Kahler currents with the Ricci curvature bounded curvature, in fact, bounded below is enough, and LP volume measure in the integral class, they can all be embedded into a same huge projective space. So for the last couple of minutes, I'll talk about applications. So this, I also want to say that all of this will work for Kahler varieties. It's in the Yale Center. We should probably talk about some string theory aspect on the Kahler manifolds. So essentially, this tells us for the complex for Kahler varieties of complex dimension 3. If it has log terminal singularities, and you solve a singular Ricci flat Kahler currents metric, it naturally carries RCD structure. and naturally it has the unique metric structure on it, which gives you the same algebraic and topological structure of the original underlying algebraic variety. So when you add on these singular Ricci flat Kahler metric, it doesn't modify, it doesn't change the original algebraic structure. It gives you extra structure on the singularity with tangent cones. All these tangent cones are the same as the original algebraic tangent cones. They're all the same. Okay? As long as nothing collapsing, whatever singular Ricci flat Kahler metric you put on, it doesn't change the original topological or algebraic structures at all, both globally and locally. So that's the connection to the Calabi applications. The first application is about a PDE theorem, because given the Monge-Ampere equation, if the right-hand side is LP on the smooth Kahler manifold, the solution is proved by Curvature and later Curvature and his collaborators that the solution must be wholly continuous. The exponent only depends on the P from volume measure. But then, if it's not in the Kahler class, if you allow the class to be degenerate, it's an open conjecture for a long, long time. It's not even known if it's true or not. So what we can show is that using geometry, so the earlier approach to prove whole continuity for a solution of complex Monge-Ampere equation is through capacity theory, and recently there's also different types of work by Bingo and Fong using a more PD approach to get certain modulus continued control and whole control. But all of these work highly relies on the fact that it's in a Kahler class. There's no degeneration. But if the Kahler class, or in the singular setting, nothing knows about continuity, whole continuity of the Monge-Ampere equation solution. So this has been open for a long time, and no one knows what the answer is. But if we look at the geometric structure, if you add a little bit geometric structure to the Monge-Ampere equation, then we will be able to get whole continuity for the solution of singular Monge-Ampere equation. In particular, we prove for a large family of Monge-Ampere equation, but let me just focus on the dimension 3 case. So suppose you have three-dimensional normal projective variety. In fact, Kahler is enough with KRT singularity, and you have a smooth Kahler metric, and big omega is a smooth adapted volume measure on X. So in the Calabi setting, this is the holomorphic volume form. So I want to look at the following complex Monge-Ampere equation. Theta plus d by phi to the power of 3 equal to e to the minus f omega. And then you have the normalization condition. And so we assume supreme of phi is equal to 0. So this is a three-dimensional complex Monge-Ampere equation over a singular Kahler space or projective space, projective varieties. All right, so in general, it's not known, still it's open if phi is wholly continuous. We know it's continuous, but is it wholly continuous? It's not known. But it's a joint work with Bingo, Curvature, and Jacobs. We show that we only need to add one condition. Suppose f is PSH with respect to some big proportion of theta. Then the solution is indeed wholly continuous. Now you might wonder what does this condition means. It simply means that if you look at theta as dV bar phi as a Kahler current, the Ricci curvature is bounded from below. So if you assume the Ricci curvature is bounded from below, or equivalently, if f satisfies certain convexity condition, then indeed the solution of the complex Monge-Ampere.
Isn't it just that f is convex?
No, it's a Puri subharmonic.
Oh, yeah,
It's
okay.
worse than convex. So that's all we, and you can have convex on the compact matter.
Yeah, that's right.
So phi, we prove this. We actually prove a much bigger, larger family. But this in dimension 3, this is the assumption is minimal. All you need is just this is LP the original problem is, and you assume f has certain positivity. Second derivative complex Hessian is sort of bounded from below. Then you get polar continuity. All right. And also another application is kind of a topological application is the characterization for the fundamental group of X if the anti-canonical class has certain positivity condition. In 1998, Mihai Palm proved that if X is a projective manifold with NF anti-canonical divisor, then the fundamental group is almost abelian. So he later removed the projective condition by placed it by Kahler. So indeed, for a Kahler manifold with NF anti-canonical class, the first fundamental group would be almost abelian. So what we can show is that for complex dimension 3, if it is compact Kahler normal varieties with a KLT pair, that means Kx plus delta is a log terminal. Suppose the pair canonical class is NF, then pi 1 is almost abelian. If it's projective, then it's no. If it's projective, then this still is no.
Okay.
I think
Can you say it's almost abelian?
it's almost like you have to look at the center, it's finite. So, so this is basically a slight generalization of Palm's result. And also, in the case of projective case, it's earlier proved by our collaborator, Jian Song and his collaborators. So our new observation is that in the Kahler case, we can still prove it.
But you expect it to be dimension independent, right?
Yeah, the conjecture is for any dimension. But we don't know. Here, it's just a very quick application of our work in dimension 3, because you can just sort of using to build a singular metric on the 3-dimensional space with which curvature from below, sort of. Then you just imitate what Palm did, and you add on to some new techniques from one which I'm not familiar. So, so Jian Song is the expert on these. He's been working on these the topic for a long time. And finally, we want to study global and local rigidity results in relation to algebraic and geometric volumes, especially with respect to singularity. We want to establish kind of geometric singularities according to these algebraic singularity theory, like ACC condition. What would be the consequence in Riemannian geometry, especially in terms of stability and rigidity, for example, related to Perelman's stability theory. That's is always also working project. So I'll stop here. Thank you.
Okay, questions for Jian? So I have a question. So it's kind of, I mean, the smooth things you mentioned work well in higher, some ingredients work well in higher dimensions, right?
Which part?
Like the smooth, yeah.
If it's smooth, in the smooth setting.
Yes. Do you know, like, what is the
you mean
reason
continuity?
Yes.
Like
Why does it become more complicated?
Well, for example, for the Holder continuity, the key is you have a good regularization. Because the solution you want to the solution phi is not going to be smooth near the singular set, the degenerate set. So in general, the solution is not even smooth or C2. So what you do is that you regularize it. There are different ways of doing regularization using Alzheimer's techniques. So the most effective one is Demailly's regularization using integral method. So it's a kind of a complex exponential map. But that highly depends on the curvature control. So near the singular set, the regularization will fail. So you can't have a quantitative control about regularization near the singular set. That's the problem. So in the business of PSH functions, the hard part is that at the degenerate set locus and at the singular locus, you lose all the approximation scheme. You can't group. You can't just. That's the problem.
I see. Okay. Any other questions? I have other questions, but maybe I would ask.
Thank you.
Let's thank Jian.